right, let's get it going. So last semester, no, last semester, I mean last week. Last week we had some fundamental discussion of mechanical design, and so tells us what's the design procedures, right? Well, we start with the problem, and we start to analysis it. What's the issue we need to solve, and then we come up with the solutions we have, and then we synthesize it, and then we find the approach, and then finally we do a presentation to see to present in front of other teams, right? That's basically how mechanical design is done, right? We start with problem and we think about the solution, and then we put together a presentation, and then we go from there, right? Okay, so today I am going to tell you guys more about load analysis. So because mechanical design, the most fundamental and the most simple or good example is beam design, right? So we'll start with fundamental, a little remind of mechanics and materials. I'm sure you guys all learned this before, and I'll just give you guys two examples to remind you about how to do a load analysis of a beam, all right? Okay, so let's see. Oh, today is better than the other day. All right. Okay, so we're going to look into load and stress analysis, right? And I'm sure you guys all learned this. You learn from statics and mechanics materials, and based on my experience, seems like most of the students hate it because it's complicated in some way, but that's very important. So we have to learn again in mechanical design, but I'll try to only spend 1 week or so on this to go over the materials, and we'll try to have some little extension above what we learned before, right? Okay, so load and stress analysis. The fundamental behind it is equilibrium. So we have a review of equilibrium and free body diagram. In short, just FBD. All right. Okay, first of all, let's see what is equilibrium. Basically, it tells us to assume there's a material system to be studied is motionless. How's my handwriting? Good? All right? Okay. If it's terrible, let me know, okay? If you can still read it, just be quiet. If you can't read it, let me know, okay? Motionless. Or at a constant velocity. All right, so motionless or at a constant velocity, they have one point in common. Common is there's no acceleration. A is 0. Okay. Now, according to Newton's second law, F equals to ma, or summation F equal to ma. When you don't have any acceleration, that tells you there's no external force, right? The summation of external force is 0. Okay. All right. So when it's motionless or on a constant velocity, we say this system is at equilibrium. Okay. Now, once we have that, once the system is under equilibrium, the way we do is always summation F is 0 and summation moment is 0 to solve for the unknowns, right? The resultant force on both points, right? Or we're trying to find what's maximum resultant force or shear force or maximum moment applied on the beam. This is what we do, right? So these two are the fundamentals of equilibrium, okay? All right. So we'll start with an example. Okay, we have a simply supported beam. Okay, point A, it's fixed. And point B is on a roller. You have concentrated force of 10 newtons. Over here is 2 meters long, while over here is only 1 meter long. Now, I'd like to ask you a question. So, seems like ever since we started mechanical engineering major class, statics, and then mechanics materials, so other things, we always look at simply supported beam or cantilever beams or analysis, right? Simply supported. Okay, so this thing over here. Now, we have concentrated force sometimes, we have distributed force sometimes, and sometimes we have nonlinear force, right, applied on the beam. And we'll always ask you what's the resultant force on A, on B, and where's the shear stress at, where's the moment at, right? So always ask you to do V as a function of X or M as a function of X, right? Remember? That's what we ask you to do all the time, right? Well, seems like most of you know with me. Okay, so pay attention to this example. After example, I'm going to ask you this question, right? Okay, so simply support beam. Now, it's asking us to find the resultant force supporting point A and B. Okay, all right. So when we see this kind of problem, the first thing we do is, of course, free body diagram, right? So start with FBD. Okay, so free body diagram, all it does is it takes the supporting force away. Okay, and you still have 10 newtons over here. and the distance over here is 2, distance over here is 1. Now if we take A, it's a pin, right? So you have 2 resultant force, AY and AX. While B is sitting on a roller, so it's free to move in the X direction, so you only have BY. Now when we take the resultant force away, we always assume they're positive. So that's why AY, BY is always going up, while AX is always going to positive X direction, right? Okay, so summation Fx is 0. So we know AX is 0 because AX is the only force in this system, in this free body diagram, right? Okay, now summation Fy is also 0. Therefore, we know AY plus BY should equal to 10 because AY and BY are going up and 10 newtons are going down. So therefore, these two added together should equal to 10, right? And there's 2 unknowns, AY and BY, so we need one more equation. So we have summation MA equal to 0. Okay, so summation MA, we artificially assume A is pinned, and all the other force will cause moment about point A, right? 10 newtons will be causing a negative moment because it's rotating clockwise, while BY will cause a positive moment because it's causing it to rotate counterclockwise, right? So, okay, so then we know the positive moment should equal to negative moment. Therefore, 3 times BY should equal to 2 times 10. 2 times 10 is the force times moment on, which is the moment caused by 10 newton, the concentrate force, while By times 3, the moment on, is equal to 2 meter plus 1 meter, right? So By has moment on of 3 meters, therefore force times moment on should equal to force times moment on, okay? All right, 2 equations, 2 unknowns, we can solve for that. So we know By is 20 over 3 newtons, and AY should equal to 10 over 3 newtons, and then that's it. That's how we solve for a simple problem like this, right? And if we go a step further, say what's the shear stress inside and what's the moment inside, we can do the same. So V as function of x, M as function of x. So AY is 10 over here, concentrated force goes back, and then you have something like this over here and over here, right? Very simple, okay? Now you don't have to remember the V and M yet. Next problem will be asking you guys to do that, okay? All right, now back to my question. So this is a problem you guys see in statics and mechanics materials, right? Yes? Okay, so now, do you guys know why we're always looking at a simply supported beam? Is it because they're simple? They're being easy to analysis? Anyone? Why we always look at this problem? In other words, why this thing is important and how this simple supported beam can be related to realistic problems. Can be buildings I-beams, right? Yes, exactly, shaft. So imagine this, a shaft is what we analyze a lot because there's lots of components on it. A shaft has 2 bearings to support it, right? Or if you want, think about a big scale. Think about an axis of a car, of a vehicle, right? There's 2 wheels. So each wheel will be similar as bearings, okay? Now, on this shaft, it transfers power. So sometimes you use gears or pulleys. Depends on what you want, right? Gears will transfer power. Pulleys will be transfer power as well. We use a pulley on the outside. So when these gears engage with each other, there's just one concentrated force applied here. Now when the pulley transfers power, there's just one force applied over here. And then when you take the bearings away, all bearing does is supporting force. Do you look familiar? Right? So that's why. Because shaft, axis are very common in mechanical design, and they can be modeled as simply support beam. That's why simply support beam is so important in our mechanical design class and also in our mechanical undergraduate curriculum. Make sense now? All right. Good. Okay. All right. Let's see next. Okay, so one of the things we want to know is what's the shear force and the bending moment, right? And I'll come back to ask you again why we need to know this, all right? I'll give you one more example. So shear force and bending moment in beam. Okay. All right. So first of all, let's see what is the problem. And I'm sure you learned it before. Just give you a quick overview and a review of it. So again, you have a resultant force on a simply supported beam, R1 and R2. You have a force F1. Coordinates goes like this: X and Y. Right? F1 and F2 and F3, for example. It's relatively speaking complicated problem. You have 3 concentrated force and 2 resultant support, right? Okay, now I set up coordinates. This is my origin, X and Y, and I'm asking you, hey, at this point, what is the internal shear force and moment? So you set up your coordinates. Let's say this is point A, and I say this is XA. Right, so all you learned before is you can do a free body diagram and also use the equilibrium to solve for the problem. So Y and X. Let's not make it that long. Just a sin over here. Okay, so we know here's the F1 and here's R1. And so there's gotta be at this point you have 2 components: shear force at point A and also a moment MA, right? So these 2 things. Okay, so these 2 things, the reason why they exist is because for a system like this, it also undergoes equilibrium. Okay, so for example, summation F is 0, so you have R1 should equal to F1 plus VA. That's because summation F equal to 0, right? So you gotta have shear force existing at a point A to counterbalance for the rest of force, right? So same thing for MA. So summation MA equal to 0, of course, this MA has to be existing to counterbalance for the moment caused by the F1, right? Okay, so therefore, at any point of the beam, you have certain shear force, you have certain moment, right? Okay. Another thing we learned is bending, right? And bending is relatively speaking simple. You have a beam like this, right? If you apply moment, it's going to bend. We call this positive bending. So if a bending moment is causing the beam to bend up, we call them positive bending. Well, if it's going to cause the beam to bend like this, we call it negative bending. All right, and for the shear force, if a shear force is positive on the left-hand side, negative on the right-hand side, it's called positive shear. Otherwise, it's called negative shear. All right. Speaking of a shear force, one of the examples I always like to say is shear force is very important. Other than cutting sheet metal, you guys probably use it since you're in kindergarten. Everybody uses scissors, right? The reason why scissors can cut a paper open is because shear force, right? There's two blades. They are not on the same location. If you look at the extraction, right? They're right next to each other. Okay, so when you close the scissor, the blades, it's going to cause lots of shear force on the paper. So that's why you can cut the paper open, right? Okay. All right. So in other words, shear force can cause material failure, right? Make sense? Scissor cut papers, paper become two pieces, and then that tells you shear force can cause material failure. Make sense? Yes? Why you guys are so quiet? Still in vacation mode, huh? Maybe we should cancel the class, huh? All right. Anyhow, so I believe in mechanics materials you learned this. If you have a beam XY and you have certain distributed load you have Q1x, you have Q2x. All right, Q is a distributed load, right? How many newtons per meter, right? Okay, and the way you do it is, say this is x1, this is x2. So the total equivalent force is just equal to F1 plus F2. And F1 is integration from 0 to x1, Q1x dx. And F2 is from x1 to x2, Q2x dx. Right? So this is how we calculate distributed force, right? Because when we do free body diagram, we have to know the equivalent force. Okay? All right. Now, in our shear and moment diagram, these two equation sets are very important. First one, dV over dx equal to Q. dm over dx is V. Still remember this? How many of you remember this? Couple of you guys? Right, okay. No worries, I'll start with fundamental, give you some examples, right? Okay. Oh, one thing I forgot to mention. Here, so the resultant force F1 and F2, you see you have to use integration to calculate it now, right? But in integration, you know, integration of a function of x is nothing but equal to the area underneath this curve, right? Integration, the purpose of integration invented is to calculate the area, right? So break those functions into very small pieces, so you add them together. That's how integration is invented, right? So that tells you if I give you a regular distributed load, either horizontal or just linear increase, you can calculate the amount of F1 by calculating this area underneath this curve. Make sense? All right, I'll try to go more details when we see an example. All right, these two equations tells you when you have a V and M diagram, you can use Q and V to determine the changing trend of the curve. And another thing is delta V equals to integration of Q dx. How do I write a Q? There you go. And a change in moment equals to integration of V. Right? So, give you an example. For example, you have a shear force diagram. Right in the middle, there's concentrated force. And you have a not that complicated yet. Okay, shear force like that. A moment would be like this, right? Okay, now first of all, let's see here. Changing shear equals to Q. Okay, so see here you have a horizontal line, so it tells you the slope is 0. So probably there's no distributed force in the system, right? And dm dx equal to V. So changing moment is equal to the shear force. So shear force over here is a positive number. For example, 5 or 10, whatever you want, right? So that tells you over here the slope of m should equal to 5 or 10. So it's a straight line. Okay, so as simple as that. And basically the reason why I mentioned these 4 equations again is we will be using it for the rest of this week. All right, so we'll be seeing quite a lot of examples, and make sure you know these equations. All right. Okay. All right. So next, let's look at an example. Am I teaching too fast? No? Good? All right. If it's too fast, let me know. Okay. All right. We have a again a simply supported beam. One of the feedback I got from my previous teaching is students always like examples, so that's why I'm giving a lot of examples now. Do you guys like it?
Yes.
Okay, good. All right. And another good thing that will make you happy is all my exam quiz will be very similar to the examples. Okay. Well, you guys don't care? All right. All right. Okay. All right. Okay, so there's a simple support beam, and in the middle there's a point. Let's call it point B. All right, so from point A to point B, the distance is 5 meters. And from point B to point C is also 5 meters. Okay, so basically point B is right in the center of this beam AC. Alright? Okay, now from let me try to write A in a different location. Okay. Alright, so from point A to point B, there's a distributed load. Oh, I need to sit. Okay, so let's see here. Now this distributed load has a magnitude of 2 kilonewtons per meter, and at point B there's also a moment applied at exactly point B. Okay, so that equals to 50 kilonewtons times meter. All right, so as simple as that. Simplest support beam with a distributed load on half of the length, and at a point B, there's a moment applied equal to 50 kilonewtons times meter. All right. Okay. So it's asking us for two things: the shear diagram and the moment diagram. Okay, so it's only asking us for two things. Should be easy. So let's see. All right, whenever we see this kind of problem, the first thing we do is free body diagram. All right, so free body diagram. So a beam can be just a line, doesn't have to be a beam anymore. And point C is sitting on a roller, so it's free to move in the X direction. So all you have is CY, right? And AX, AY is the resultant force at point A after you take the pin off. And this distributed force is still there. And with a magnitude of 2 kilonewton per meter. And at this point, you still have a moment equal to 50 kilonewton times meter. Okay, that's it. That's how the free body diagram is done. And solve for the unknowns, right? Three unknowns: AX, AY, and CY. And what we do is the same thing. Summation fx is 0. Therefore, AX is 0. And summation fy is 0. Therefore, AY plus CY going up, right? There's a two positive force, so equal to the negative force, which is the force caused by this distributed load, which equals to 2 times 5, right? 2 times 5. Okay. Lastly, summation MA is 0. So that we know positive bending moment should equal to negative bending moment, right? Okay, so see here, one of the things I always like to do is sometimes you might ask me, hey, why you pick A? Why don't you just pick B or C, right? Now, I look at this free body diagram. Whichever point has most of force, I just pick that point because you can ignore lots of force, right? So I just pick A. So looks like distributed force is going to cause a negative bending moment because it's rotating clockwise. So negative. All right, so here you also have 50 kilonewton times meter applied at the point B. So it's also negative, right? The only positive bending moment is caused by C, which goes up. So it's caused the entire beam AC to rotate counterclockwise, right? All right, so now I know. So let's say 10 times 2.5 plus 50 should equal to 10 times CY. Okay, so just on our side, when you have a distributed load it's equivalent to a force in the center. If it is below, the magnitude is the same everywhere, right? Now the magnitude of force equals to 2 times 5 equals to the distributed load magnitude times the total length. And the location equals to exactly half. Okay, all right. So that's why the bending moment induced by this distributed load is equal to 10 times 2.5. Okay. Otherwise, it's hard to calculate. So you have to transfer this distributed load into a concentrated load, and the location is right in the center because this distributed force is uniform everywhere. Okay. All right. Just on a side, I'm sure you guys all know, but I just want to make sure. Okay. So 3 equations, 3 unknowns. So we can solve for that. So AX is 0, CY is 7.5 kilonewtons, and AY is 2.5 kilonewtons. Okay, so that's my free body diagram, and that is how I solve for it. Let's see here. So it's asking for the shear and bending moment diagram, right? So let's start from here. CY is 7.5. AY is 2.5. Distributed load 2 kilonewton per meter going downwards. Bending moment 50 kilonewtons times meter over here. Okay, so separate them a little. This is a fully solved free body diagram, right? Now next, I'm going to show you. Just to remind you, we can use these 4 equations right here, to fully solve for the free body. And coupled with free body diagram to solve for the shear and the moment diagrams. Alright, so first of all, shear diagrams has a unit of kilonewtons. Okay, so first of all, you look at it here, you have a supporting force of 2.5 kilonewtons, right? Okay, so it started at 2.5. This point is 2.5. And we know one of the equations we just got to know is dV over dx equals to q, right? Okay, so once we have this, we know we have a distributed load over here, and it's 2 kilonewtons per meter, and it's also going downwards. So possibly it's going to push the shear diagram going downwards. Until at the center of the point, right? And because of the Q is constant, so therefore it is a straight line because the slope of the line is constant, right? Okay, now there's 2 interesting points I want to solve for here. First one is here, second one is here, right? So I want to know at when it reaches 0, and at at half, how high of the shear force gets up to, right? Okay, so next we're going to solve for these 2 points. Okay, so these are the 2 equations we are using now, right? this equation tells you where this line is going, while this equation tells you how much it is going. Okay? Alright, so we want to know what's the coordinates over here. So we need to use this equation over here. Delta V equals to Q dx. Alright, so what we know is the changing in shear is from 0 to, from 2.5 to 0, right? So the changing shear ending point 0, starting point 2.5. So delta V equals to 0 minus 2.5, right? So ending point minus starting point. All right. Now another interesting thing is, like I mentioned, integration is nothing but an area, right? Okay, so we know the 2 kilonewton per meter is the width of it, and then length, how long it is, I can calculate from here. So this equals to 2 times x1. x1 is exactly what we are looking for. Make sense? All right, so that give you answer. X1 is just equal to, oh, I forgot to put negative sign over here because Q is going downwards, so Q is negative 2. So X1 is 1.25 meters. So okay, so we know here. Mm-hmm. $1.2. All right, so this is 1.25 right here. Okay. All right, and the next thing is I want to know this point. What's the value on the y-axis, which is the shear force, right? Again, we use the same equation. So delta V equals to integration Q dx. Now this time, let's say this is point B of VB. Okay, so VB is the ending point, and the starting point is 0. So that equals to 2 times whatever length over here from this point to this point, right? So we know that length is 5 minus 1.25 because the total length from here to here is 5, and we already know 1.25 is the length over here, so the rest of it will be the length, right? Okay, so VB, if you calculate that out, equals to 2 times 3.75 . Okay, and with a unit of kilonewtons. Now again, see, this VB is supposed to be negative, and the reason why it's not negative is because this Q I'm using positive 2 here. Alright, so just be careful. Now I always like to use positive numbers because by looking at the plot, I know exactly whether they're positive or negative, right? So 7.5 is where this VB is at. Let me try to write it better. Okay. All right, so halfway done, right? So the next will be what's going down from point B to point C. So from point B to point C, we can still use these two equations, right? So dV divided by dx is Q. What is the Q from point B to point C? 0, right? So if you have a slope of 0, what's the line look like? straight line like that, right? Okay, now at the end, at point C, you have a concentrate force 7.5 pushing up. So it's going to go back to 0. Because this is negative 7.5, should say negative 7.5, and here it goes up 7.5 because whenever you have a concentrate force, it jumps the magnitude of the concentrate force, right? So minus 7.5 plus 7.5 should equal to 0, which totally makes sense. Okay, so this is your shear diagram, as simple as that. Next is the moment diagram. So moment, let's say we give a unit of kilonewton times meter. Okay. All right. So one other thing about moment is if look at free body diagram, when you have a concentrate force at the end, the starting point and the end point, so your shear diagram doesn't start with 0. Okay, so see here start with 2.5 and here ends at 7.5, right? So when you look at the free body diagram, if there's no moment at the end, that tells you at both ends the moment will be 0 too, which totally makes sense because summation m is 0, right? At these 2 points, point A and then point C, summation m is 0. So at point C there's no moment. At point A there's no moment. So it should start at 0 and end at 0. So we already know 2 points on the moment diagram. 0 and 0 at point A and point C, right? Okay, now we can also use these two equations to solve for where the moment diagram is going to and how much it's going to go up or go down, right? Okay, all right, so we need to, this time we need to use the shear diagram to solve for the moment, right? So first of all, dm over dx equal to v. So that tells you initially the dm over dx is positive because your shear diagram starting from the origin, it's 2.5. Slowly decrease to 0, right? That tells this line has a slope. Initially it's 2.5, then eventually it's going to be 0. So possibly, let me just draw the line here. It's going to be like this. Right? So initially, because if you look at this parabolic shape, do the slope. Initially it's high number, then slowly the slope becomes 0, right? Because dm over dx is nothing but slope of the v. Make sense? Okay. All right. And again, the interesting thing is I want to know what is the value at this point. So delta m is integration of v dx. Okay, so v dx, like I said, integration is nothing but calculate the area. So the area of this shear force over here is a triangle. We know how to calculate the area of a triangle, right? The triangle is equal to 1 over 2 times 2.5 times 1.25. And that, what is 1.25 times 1.25? I don't have a calculator. Can anyone help me to calculate this out? 1.25 times 1.25. What is it? 1.875? Kilonewton times meter. Thank you. 1.875. Right, so that's how it's calculated. Let me just erase this because I still need the space. I try to write it over here, right? Because
we didn't get that answer.
Huh?
Yeah.
What?
1.5625. I didn't get that one.
Well, who told me it's 1.875? What's your name? I need to deduct some final grade points from you. Equals to what?
1.5625.
No, I'm just kidding, alright? Yeah. Right? Yeah. Okay. Alright. And a unit is kilonewton times meter, like I mentioned over here, right? Okay, so let's see. Next, again, we want to know where it is going. But in terms of where it is going, we use this equation, right? dm over dx equal to v. So, okay, initially the slope is 0 because v is 0. And then it becomes a negative number and then higher and higher and higher, right? So that tells you initially it's going to decrease a little, then decrease more and more and more and more and more. That's how it's going to work, right? Okay. So we know it's probably going to look like this. Something like that, right? Goes down deep. Okay. Now, again, there's a interesting number over here. We know this is 1.25. I'm not going to write a unit, alright, because it's too small. So 1.25 just meter, right? I guess better write it. So again, 2 points I'm interested in. The point over here and the point over here. I want to know at what coordinates on x it touched 0 again, and at the end of the half, how down it goes, how deep it goes down to, right? So in terms of calculate this, it's easy. Delta m equals to integration v dx. Now delta m is 1.5625 minus 0, right? Because this point is 0, this point is 1.5625. Okay, now again v, the way we calculate v, wherever you have x, the shape on the area under the v is a triangle, right? So when you have a triangle, it's always 1/2 times a times b, right? So whatever is a over here, whatever is b over here. Now, by looking at it here, take a wild guess. What will this x2 be? x2. What this value will be? Huh? 1.25 as well, right? Of course. Why? Because this is symmetric. Because I'm calculating area, right? If I want to find a triangle, which has the same area as this red over here. It's terrible, huh? Let me try to, how do I do redo? Oh. Let me just do it like this. Sorry about that. Huh? Oh, here? Oh, awesome. Now I learned some new tricks. Okay. Alright. I'm learning something new this semester as well. That's perfect. Good. So if I want to find a triangle over here which has the same area as this one here, possibly the x should be the same because these two triangles, they are the same in terms of area, right? So if I have 1.25 here, the x2 should also exactly equal to 1.25 meters. Okay? All right. Very good. So the next thing will be how deep this thing goes down to. How deep this thing goes down to, all right? To find that out, we use delta M equals to integration V dx. Now we know this integration of V dx is nothing but just the area of this trapezoidal here, right? So let me try to use a different color pen. There you go. This is what I'm looking for. Whatever inside this red box will be delta M equal to, right? Now I can do something better. This yellow triangle should equal to this blue triangle, right? Okay, so see, I'm trying to calculate delta M, so therefore I know this MB over here, right? Now the equation I use is delta M equal to integration V dx, right? Because MB minus 0 this is 0, right? MB minus 0 should equal to this red trapezoid over here, this area. Make sense? Right? Integration V, right? Okay, so that's easy. How do we do this? Trapezoidal shape. This length over here is 7.5. This length over here is 2.5. And the height is 5 minus 2.5. So this is 2.5 from here to here. Okay, now this is rectangular, this is rectangular. So I know the length here, I know the length here, and I know the height. Of course, I can calculate the area, right? So the area, let's just say A for area. Area equals to 1 over 2, 2.5 plus 7.5 times height equals to 10, 5 times 2.5, that's 12.5 kilonewton times meter. Make sense? Right? So this area is 12.5. Okay, so this is negative 12.5. Yes, at this point, right? Any questions? No? Okay, now something dramatic is going to happen. Look at it here. Point B also has a moment applied, which is 50 kilonewtons times meter, right? Okay, now when you have a moment applied here, of course, at this point, it's going to have a counter moment, which will be same magnitude but different direction to counterbalance for this moment. Makes sense, right? Okay, so we know this is a negative 50 because they're clockwise. So there's gotta be a positive 50 kilonewtons times meter applied, existing inside point B. Okay, so we'll have a sudden change of positive 50 from B bend, going to jump way high over here. So that's 37.5 y minus 12.5 plus 50, okay? Because you have 50 kilonewton times meter of moment, right? Okay. Times meter. All right. It's just like when you have, when you have a concentrated force, it goes back, same thing, right? When you have concentrated force, you have a jump in shear, where you have a concentrate moment, you have a jumping moment diagram. Okay. All right. Now the lastly, is lost from point B to point C. From point B to point C, V is constant minus 7.5, right? So we know that's a straight line, and like we mentioned, it's going to go back to 0. So this is what it looks like. Okay. Now I can double check that, see whether it go back to 0 or not. So what I do is again, delta M equal to V dx. Now this time, the area underneath that is just rectangular. That's easy. 7.5 times 5. 7.5 times 5. And we say this is 37.5 exactly, right? Okay, so of course it's the same, right? Because delta M changed from 37.5 to 0, and the area underneath that shear curve, shear diagram is a rectangular. That's also equal to 7.5 times 5. The same number, right? Make sense? Okay. All right. So this is how it's calculated. Any questions?
Where are you posting your videos at?
Huh?
Where are you posting your videos at?
Oh, speaking of videos, last time it didn't get recorded. I apologize. Well, I'm trying to use a new software, right? And the first time it never works, right? It's kind of like when you do an experiment, right? Well, this time it is recording. I hope so, right? I am going to post it on the YouTube channel of Mechanical Engineering. Search for that, right? Search for UTEP Mechanical Engineering YouTube channel. And I believe there's already some videos over there. And I'm going to do the same to post it on the YouTube channel, right? Speaking of that, let me check whether it's recording or not. Give me a minute, okay? Let's see.
I make it